All right, hopefully right now you guys are kind of remembering special right triangles after watching that video. I wish I was there to see how many of you kind of remember the stuff or don't remember the stuff. The one thing I want to push is this isn't hard. It's just not hard. There's a real basic relationship of 4 consecutive numbers. If you think about it, what you have here is if I call the shortest side of a 45, 45, 90, or the shorter legs, call that square root of 1. The hypotenuse is square root of 2. If the shorter side here is square root of 1, this is square root of 3, and then this is square root of 4. And so really, I just see this consecutive growth right here, okay? It's real simple. And if I think about the relationship of these 3 numbers of square root of 3, square root of 4, square root of 2, clearly square root of 4 has got to be bigger than the square root of 3. And the hypotenuse of a 30, 60, 90 is bigger than the longer leg. And so this should hopefully help in some ways. The 45, 45, 90, the magic number you have to remember is square root of 2. And in a 30, 60, 90, you just really need square root of 3 and square root of 4, knowing that square root of 4 is the biggest. And so therefore, that's always going to be related to the hypotenuse. Okay, so what I'm going to do is try to go through the answers of these real quickly. For number 1, it said the shortest side is 1. So therefore, the longer leg would be square root of 3 and the hypotenuse would be 2. Okay, next, it said the shorter side is 3. So therefore, the longer leg would be square root of 3. 3 times the square root of 3, and the hypotenuse would be 6. Notice I refer to them as shorter leg and longer leg. The book says side opposite of 60 degrees, or the worksheet that I gave you was based off of a book that names it that way. And so I'm sorry if that was confusing. But I in my mind, I think short leg, long leg, hypotenuse. All right, the next 2 involve the hypotenuse. It says, okay, this time the hypotenuse is 8. Well, if that's the case, then the shorter leg's got to be 4. And again, the longer leg is always that times the square root of 3. This time it's an odd number, so it doesn't divide evenly, but that doesn't make it any harder. We have 5, so therefore this is 5 halves, or 2.5, and therefore this would be 5 times the square root of 3 all over 2, or 2.5 times the square root of 3. Either way you go. All right. And then these are probably the oddest problems, are when you start with the longer leg and you got to work your way around. The longer leg is 6, and this side is 6 divided by the square root of 3. That's the relationship. If you're going to the short, you have to divide. And then so therefore that makes this one 12 divided by the square root of 3. Now, you and I both know that this is not how we want to leave this. We want to multiply the top and bottom by square root of 3, and that would give me 6 times the square root of 3 over 3, which then would be 2 times the square root of 3. And if this is double, then this is clearly 4 times the square root of 3. Okay? All right, next, let's see here. The last one of this section, the longer leg is 4. So if this is 4, then this is 4 divided by the square root of 3, and this is 8 divided by the square root of 3. Now, you can rationalize that and get 4 times the square root of 3, or if you rationalize the denominator, but it doesn't make it any prettier. So there you go. Okay, now let's look at the 45, 45, 90s. 45, 45, 90s look like this. For the first bunch, we were told, okay, hey, this leg is 4. So what's this other side? 4. And the hypotenuse is 4 times the square root of 2. That's simple. Okay, number 2. This time it says, well, this time the shorter leg is 1/2. Well, then this other leg is 1/2, and this would be 1/2 times the square root of 2, or square root of 2 over 2 is the same thing as 1/2 times square root of 2. All right, number 3 says this time we're at square root of 6. So this side would be square root of 6. And this side would be square root of 6 times the square root of 2, which is the square root of 12, which actually simplifies down to 2 times the square root of 3. Okay, so that would be the actual size of the hypotenuse is 2 times the square root of 3. And yes, I want you to get to that. All right. Next, we've got 6 times the square root of 2. So this one would have to be 6 times the square root of 2. And that would make this 6 times the square root of 2 times the square root of 2. And square root of 2 times square root of 2 is 2. 6 times 2 is 12. So that hypotenuse would be 12. All right. And for the last 2, we're given the hypotenuse. This one we're told is 8. So therefore, this is 8 divided by the square root of 2. If you rationalize the denominator by multiplying the top and bottom by square root of 2, you get this, which is 4 times the square root of 2. So that's the same thing for this one. Pretty simple. And lastly, the very last problem on the page says, let's see here. It says that this is square root of 6. Well, that would make this square root of 6 over the square root of 2, which is the same thing as the square root of 6 over 2, which would be the square root of 3. Okay, and so therefore this is square root of 3. All right. And yes, I want you to get all the way to that. All right. So here's the deal. I'm going to have you work on some problems, and this next set of problems are going to all involve some really basic geometry. Okay, it's going to involve the sum of the angles inside a triangle, and it's going to involve the Pythagorean theorem. And that's it, okay? And so, like, for instance, if I gave you a triangle, whether it be a right triangle or any kind of other triangle, it doesn't really matter. The angles inside a triangle always add up to be 180 degrees. Doesn't matter what the triangle looks like. So if I give you a situation like this, okay, and said, hey, this angle right here is 120. This angle up here is 30. Let's see, and this angle right here is 40, okay? And if I said that this was X, this was Y, and this was Z, you should be able to figure out all three of those, okay? For instance, I know that I can figure out X because X plus 120 plus 30 all have to add up to be 180. And so that would mean that X plus 150 has to add up to be 180, so therefore X has got to be 30. Okay, for Y, I can see that these two angles are supplementary. They back to back, and so as to make a straight line, so they must be supplementary. So I know that Y plus 120 must add up to be 180. Subtract the 120 from both sides, and Y is going to be 60 degrees. Okay, and if Y is 60, then I know that 60 plus whatever Z is plus 40 all has to add up to be 180. Well, 60 and 40 is 100, so I know Z plus 100 equals 180, which would mean Z is 80 degrees. Whether it looks like it or not, that would be how it has to be. Okay? Now, what I want to do is I want to throw a little bit of an odd problem your way, but it doesn't make it hard, okay? So let's imagine that I had some kind of funky looking right triangle. Let's see here. We'll make it look like this and like this. Okay, and like this. All right. And we're gonna add one weird notion to this, and that is we're gonna put a big circle right here. Okay, not bad. All right. We're gonna scoot that over to right there. Okay. And what I'm gonna say is let's try this and say that we know that this part right here, oh, that's too fat. We're going to say that we know that this side right here is 8, and that side right there is 4. And the question would be, well, what's the radius? What is the radius of this circle? And I'm saying that that is a right triangle. I'm saying that this is the radius, that this is the center right here. And so I'm saying, well, what's the radius of that triangle? You might look at this and go, man, that problem's insane. And it can seem really weird, but this is a basic Pythagorean theorem problem. We know that the Pythagorean theorem says, hey, if you got a right triangle, the three sides of every right triangle always fit into the formula a squared plus b squared equals c squared. And so that's true for this case as well. If this one right here is r, then this right here is r as well. And so then plugging that into the Pythagorean theorem, I would know that 8 squared plus r squared is equal to 4 plus r squared. Now, you have to remember that you have to FOIL that one, okay? And so you go, well, this is 64 plus r squared is equal to, let's FOIL that one. And I'll switch the r and the 4 around, make it r squared plus 8r plus, 16, okay? And now look, when I go to solve this and I subtract r squared, it cancels out on both sides. And so I'm left with 64 is equal to 8r plus 16. I subtract this 16 from both sides, and I get r is equal to 48. Divide, and I get r is 6. That's easy. I mean, that was a really easy problem. And so in this case, this is a true scenario where r would have to be 6. Okay, so we're going to see some problems like that, and I need you to be okay with looking at Pythagorean theorem from a slightly different perspective, okay, where all of a sudden you have this look, and you just have to go, even if I don't know this, I know that this whole side is 4 plus r, so that's why I wrote it as 4 plus r. I know I have to, if I'm going to square that, I have to FOIL it out, okay, and we can do stuff like that. All right, And so if you can understand Pythagorean theorem and understand that the angles inside a triangle always add up to be 180, this next set of problems won't be hard at all.